going, so please continue to ask questions. Today, got it. Today, it's going to be a bit different than yesterday in terms of focus. So my plan was to have yesterday really be dedicated to the background on Imandra. Today is industrial applications, and I'm going to principally focus on the financial ones, but I can give you some intros to a few others if we have time, like autonomous vehicles. And we're going to stick to that mostly, but I want to do just a short recap because I talked to a few people who missed yesterday or parts of yesterday. So I want to do a quick recap. And then there were a couple things that I didn't show you that are relevant for getting started with Imandra. So I'm hopeful that in the next 10 minutes, we can effectively finish the background, and then we'll get on to applications. So, okay, let me just remind you. So, what is Imandra? Imandra is really these three things together: programming language, which is a pure higher order subset of OCaml, a mathematical logic. So effectively that incorporates formal semantics for OCaml for our fragment of it, and then effectively mathematical tools for reasoning about it, and then a reasoning engine which tries to automate the application of those tools. And we went through a bit yesterday of what we call first-class counterexamples. So really, if you have a goal in Imandra, a goal is itself a computable function, a Boolean valued function. And because your whole model in Imandra is a program, a counterexample corresponds to some input that causes your Boolean valued function to evaluate to false. And in Imandra, one of the things we're doing constantly effectively when you're analyzing conjectures is symbolically looking for counterexamples. And we went through yesterday a bit about how this works in the context of recursive functions, polymorphic types, and things like that. But big thing about these counterexamples is their first-class nature. So let me just remind everybody. I'll show you. Oh my goodness, how do I get out? Okay, what that means, and oops. Basically, if we have some goal here, like verify for all functions f and all values x, list.map of f over list.reverse of x is not equal to 1, 2, 3, and we get out a counterexample. Key thing is this counterexample, in addition to being found automatically, it's actually synthesized as code, and you can compute with it. So I directly have a module here called cx. It has this value cx.x. It has a function, and I can now effectively take what I tried to verify, which in this case wasn't true, list.map of f over reverse of x. And a little trick in OCaml, you can effectively use a module to give a namespace locally if you do this. So I can now do cx dot, and I can always just evaluate exactly what I had put in my goal. Maybe I'll just do this part to show you. And now this is going to be evaluated. It's like a local open of the cx module. So the f is going to be cx.f. The x is going to be cx.x. And I see that's 1, 2, 3. Okay, so that's what I mean to be first class. Counterexamples are there. For simple things, this looks cool, but it's like, what's the big deal? But the big deal really is when you have industrial models that are huge, and these counterexamples themselves. Okay, these counterexamples can be absolutely enormous. We'll look at some today. Long sequences of messages into a complex system, trading system, for example. And you really want one environment where you have your executable model, you have your counterexamples, you can directly run them on it, trace things, and so on.
So as with one of the examples this morning, one of the things that at first sight looks a bit weird here is that your counterexample is based on the type with 5 elements, not 3.
Yes, it's not minimal.
And defines a function. You talked about having the default case, so I might expect 3 others to do real work, as it were. But it's weird that it's not minimal. And so if you have a big model, how do you make sure the counterexamples are small enough to be intelligent?
Fantastic question. So I'd say this only comes up with polymorphic types. It's only in the case when effectively that, when we start looking for counterexamples, we first monomorphize. So we introduce Skolem types for all the polymorphic type variables, and then we specialize to first order. So we effectively come up with synthesized first order definitions that incorporate all of the higher order things as, potentially ambient Skolem functions, right? It's no longer an argument to a function, it just exists. And we're gonna ultimately compute constraints on it and try to synthesize it. And this is basically, it's a byproduct of our congruence closure, but it's typical that the number of equivalence classes in congruence closure here, where we read off the elements of these types, only when we are synthesizing values for a Skolem type, may not be minimal. And it's one of the long outstanding things to just do a process over that to minimize it when we can. But we just haven't done that. And so you may not be minimal. A lot of SMT has this issue with related things. Sorry. Well, okay. I will just say, yeah, but basically, yeah, that's only in the context of Skolem type. So let's say we gave this a type. So we actually said F was int to int. Oh, sorry, go back to verify. F is int to int.
Oh, wow.
Then this doesn't matter effectively, because now we don't have to synthesize a type. So we're, now we're just in the realm of existing types. And I would say, even though a lot of code for industrial applications obviously has polymorphic functions involved, almost always the actual goals themselves are not polymorphic because, yeah, things have been totally grounded.
So when you say Skolem type, that's like have a polymorphic type variable A, you just make a variable called A. It's not polymorphic.
Yep. Yeah. It's a variable for the type in a sense. And it's just like, you can have a functional argument to a higher order function F. And as long as F is used in a sufficiently tame way that we can specialize its use to a first order function, then you can actually, it's the same sort of trick. You introduce an uninterpreted function F that's a Skolem function that is just in the air. It's, ambient, but it's not an argument to the function anymore or to the goal. And then we're going to reason modulo, that in a first order way. But did that answer your question? Yeah, so that really only comes up the non-minimality in the context of polymorphic goals, but that's an interesting research question to minimize those things. Yes.
So what can you do with those coverage levels? Can you see what I in files?
Yeah, great. Okay, this gets something else I want to show you. Fantastic question. So these are real values. You can compute with them. You actually, so right now I'm showing you working what's called Imandra's logic mode. And in logic mode, this is the default. The prompt looks like this, has a hash like normal OCaml. Everything you define has to be admitted into the logic. So if I try to define let rec f of x equal f of x plus 1, for example, Imandra comes back and says, error, I can't prove that this terminates. Are you sure that it terminates, right? And of course, this guy really doesn't. Likewise, you can, there are a lot of things you can do in normal OCaml, load in arbitrary OPAM packages, like OCaml packages, that you just can't do in logic mode, right? Because those functions haven't been admitted into the logic. But what you can do is you can go into so-called program mode. And in program mode, now you have access to all of OCaml. So I can, let's see. Is that it? Yeah, okay. Always forget the invocation. I can list all these available packages. I can load them. I can load a JSON module, different threading, whatever I want. I can do it here. And whatever I define here, like I could define that same crazy function here. And of course, this isn't going to be pretty. We'll get a Stack Overflow. Oh, no, we won't. This is effectively Taylor cursive, but doesn't terminate. I can do that here. I can do whatever I want here. And the key thing is it has access to all of the things that I had done in logic mode. So it still has that CX module. Crucially, we have a history in Imandra, event history. And by default, you're just seeing what you did after the system booted. But I can do history full, and I can see everything all the way back to, the Big Bang of when the system first booted and we first installed directives. And then we defined, logical operators. And then the crucial first module that we define is ordinal. So this is our, formalization of ordinals up to epsilon 0. So you can go in and you can see, the whole history. So everything you do is there. And a lot of, to get to your question, a lot of the industrial uses of Imandra will basically use Imandra with functions defined in logic mode to do some analysis of a model, something. But then we want to extract information from that analysis and turn it into, a test suite, or turn it into documentation or some other certification artifact. And you then can just go into program mode and write all your, your harness there that's doing all of that sort of industrial interface work. And it never will pollute logic mode. And so, I could define here again, let crazy, X, maybe whatever, I'll just do the same thing. Crazy X equal rec crazy X plus 1. I can do that here, but now if I go back into logic mode, if I try to use crazy, like let G of X equal crazy of X, it won't work. Oops. It won't work for a good reason there, but for a more interesting reason here, because it wasn't defined in logic mode. So it's not available. And there are some ways to go back. So you can define a function in program mode and actually in some ways interface with it in logic mode if you mark it as what's called opaque, where all is it's like an uninterpreted function of the type. There are some things you can do that can be useful, but obviously keeping all of that sound, there are a lot of restrictions. Did that answer your question? Okay. Yep.
Sorry, this is more of a basic question, but I noticed when you were verifying that that statement to do with the list of maps, that
Yes.
for example, you're essentially proving like a universally quantified statement, but the binder that you're using is just a standard fun binder, which is just lambda. So you don't have any quantifiers.
There's no quantifiers. Yeah. So it's very much like primitive recursive arithmetic, or a great kind of book expounding how to do mathematics really in this way is Goodstein's recursive number theory. But it's basically, it's a quantifier-free logic. And really the logic takes place at the level of terms. There's no separate, class of quantifiers or anything like that. And everything is about real, computable functions. So if a goal is, effectively a lambda, it's a function that evaluates to a Boolean value. And, to show that kind of explicitly, I might define something like let goal X equal, we can do our example from yesterday, list.reverse of X equal to X. So that's just a Boolean valued function. And here's a big way too, when you're interfacing tools with Imandra. So we have a module called verify. So verify.top, this is really an OCaml module. You can, this Imandra lib is an OCaml library. You can build tools against Imandra that use this interface. I can say verify.top of goal, and I'll give it a hint. And I'll say hints.auto. I think that's going to be right. Oh, what did I say? Hints, plural. Hints. Okay. And so there, notice now, because I called this function really through the API, I actually get out, this is an actual proper data type. If I had enabled actually returning proofs, I get a proof there, I'd get a proof graph here, just like we see when we go to Jupyter Notebooks, when that stuff is depicted. So yeah, I'm not sure whose question I was answering. Sorry. Yeah, okay, great.
So then that verified function is taking that function and proving that
It always will evaluate to true.
Is true.
Exactly.
Okay.
Yeah, exactly. So a theorem in Imandra, when I say it, QED, a theorem is proved, I prove that a certain Boolean valued function always evaluates to true.
Okay.
So the count examples, are they concrete or symbolic, and do you return all of them?
Great question. They're concrete. They're found, typically in a very symbolic way, but once they're synthesized, they're concrete and they're turned into actual concrete values. And by default, we're just getting one. But you can do cool, maybe I'll show you later, but yeah, you can do cool stuff like, you can define a goal that's higher order that takes a predicate, Boolean valued function and an in, and will return, in models, in distinct models. And there's a really cool way to do that cheaply in Imandra, exploiting congruence closure. Maybe I'll show you.
Do you always use a goal to do verification, or can you verify the function itself in terms of like termination or whatever checks you can put in, like assertions?
Great question. Yeah. So, I mean, when functions are defined, they have to be proved terminating, and we analyze them for, termination to make sure we really get a conservative extension. We're not introducing inconsistency, but also to figure out how to do induction involving them. But there isn't, a lot of sort of, especially imperative, program logic approaches. You'll have a notion of like a sequential statement where you have an assert or something. And that in Imandra's logic, there is no such thing. You can compile, something into that. No exceptions, yeah. So it's really pure. You can model exceptions, but again, that's going to be through something at various levels of elegance that ultimately has to keep track of state and thread it around. Okay. What else? All right, so I think that's enough just background of Imandra. We went through automated induction, and we can talk more about that. I know one last thing I want to show you, because I got some questions about this yesterday, and that is ordinals. So if you're in Imandra and you want to inspect anything in the history, you can go all the way back to the beginning of time with this history full, and we have this ordinal module. So let me just show you. You can do, show me ordinal, and we need to define ordinals before any recursive function is defined, because ordinals are used for termination proofs. So just to show you, what does this core relation look like? And this is our, special axiom, the original well-founded relation we use for proving all other functions terminating. And it's this, it's complicated. It is strict less than relation on ordinals up to epsilon 0 in a variant of Cantor normal form. But you can think about them as polynomials, basically, in omega, towers of omega, but always finite, and additions of those and so on. And then we have various primitives that when you do have difficult functions to prove terminating, you'll often use things like ordinal dot pair. And this will take two ordinals and pair them for you. So we could do something like, ordinal dot omega plus omega to omega. Ordinal, I might pair omega plus omega and omega. Let's see. So this is just something where if you, are doing some interesting inductions or interesting recursive functions that Imandra isn't able to guess out of the box, you're going to get to know the ordinal module. And if you want, even when you do structural recursion, there are ordinals behind the scenes. So if we again define like our little reverse function, I can do, if I just do it like this, you're not seeing anything about the termination proof because it was so easy. But if I undo that, by the way, you can always undo things in Imandra in the history. If I undo that and I say auto, effectively, that's going to send it to the inductive waterfall and just show us the proof. And then you can see the actual ordinals involved. And, these things, depending on how complex your functions are, these can be complicated. But it's a good thing to know. Like that is core to the foundational system is this formalization of ordinals.
So do the ordinals relate to the proofs that you're doing somewhere using induction?
Absolutely, yeah. So whenever, let me show you an example. So basically, yeah, this connects to another question that I had. In Imandra, we're quantifier free, right? So how can we possibly be expressive enough to say things you want to say? And the kind of trick, the mental, in some sense, psychological trick, it's twofold. On the one hand, we talked about this a little bit yesterday, to even ask your question, you typically have to encode so many concepts as computable functions that you then, give Imandra so much information for it to figure out how to do induction. And so that's typical when you have a statement of the form, like for all X, there exists a Y. You can't directly pose that in Imandra. So what you do is you define a function that for a given X will compute such a Y, and, really a Scaling function. And then you prove that Scaling function does the right thing. But by giving us the witness there, that actual Scaling function, we now know a lot about how to do induction. So this is how, for example, this is a development in Imandra. Really, it's just a cool exercise to start from scratch with natural numbers, not using any decision procedures for integer arithmetic, really from nothing, from just the definition of, type nat equals 0 or successor of nat, and develop some number theory. And so this goes through and ultimately culminates in this uniqueness of prime factorization. That, if L1 is a list of primes, L2 is a list of primes, the product of those two listed primes are the same, then L1 is a permutation of R2. Of L2. So in Imandra, now this is an encoding of what we would think of as a for all exists statement, but of course it's quantifier free. And the trick is that we're really every step of the way writing programs that are witnesses. And I ran this, if I can find it. Yeah, so just to show you, this is running that whole thing from scratch. And you'll see, for example, what are we're introducing a function here, and we have to use some pair measure. And ultimately it's involving a less than on natural numbers, and it ends up involving some complex ordinals. And so this has a lot of sub goals, for example. But the key is, if I now go, let's look in the history, look at all these lemmas. If I look at, let's see, difference, for example. So difference takes two natural numbers, but notice it has a measured subset with only one element, right? X. So it has X and Y as arguments, but measured subset only involves X. And basically what that means and what's happened is, in defining difference, the ordinal valued measure we use for proving termination only needed to involve X. And so basically that means when it comes time to do induction, X effectively is going to essentially play into the induction, in a way that respects the way the termination proof went. Basically we use the same ordinals that we use in the termination proof, same measures. And then we're free to do whatever we want with Y, effectively. So basically, yeah, the whole justification in a sense of induction is through, products of the ordinal valued measures that were used to admit the functions involved in the induction. And ultimately, it's the subsets of those variables that were used in proving termination that then we have to pay attention to, when we're making sure an inductive argument is correct. That makes sense. Does that answer your question? Okay. All right. So,
Thank you.
yeah, sure. So now what I want to do is move on to industrial applications. But before I do that, any last question on the sort of foundational stuff? Do we? Yeah, you can't, we're not all of higher order logic. We're this computable, specializable fragment, but, I might do something like, whatever, map length. So it's just the list dot length of list dot map of F over X is always equal to list dot length of X. Let's say, so you can prove higher order theorems for sure. And, I could turn that into a rewrite rule. We do higher order rewriting as part of our rewriter. But, this has to be something that's specializable ultimately into first order logic. So if your definitions aren't always going to be specializable, Imandra won't admit them. It's part of the definitional principle that we make sure everything you define, we can then reason about. But you can't do everything. And for example, you can't, OCaml won't let you do this either, but you can't ask about equality of functions. So I can't do this. I couldn't define something that takes two functions, let G of F equals, let's say, Imandra won't let me do that.
An example could be this, the reversing. That was almost very
Say it again, sorry.
the reversing.
Uh-huh. It's proving that two functions are equal when applied to values for all X, F of X is always equal to G of X, but it's not saying that, F is equal to G. So that's a big distinction. Yeah. So we can't talk about equality of functions, full stop. But what we can talk about obviously is always, equality of functions applied to variables or to values.
Kind of like vice.
Yeah, and by the way, that's, of course, reverse of X and X, those two things being equal, it says nothing about the computational work. Reverse of X doing a lot more work.
So we don't have functional extensionality.
No, I mean, in a sense, it doesn't even make sense because we can't talk about equality of functions. We can, yeah, it's much lower level. And in a sense, it's that restriction to concrete, in a sense, we inherit this from the fact that you can't compute that. Say it again, sorry. Yeah, we can do that. Exactly. We just could never conclude then that F is equal to G, for example, because we can't even type F is equal to G. Okay, cool. All right, now want to go into industrial applications, and I'm going to focus really first on financial ones. Let's see, we have 15 minutes before a break. So, okay, so if anybody wants to learn about this in more detail, I'm really talking through a paper that sort of set out this program of what we do in finance called formal verification of financial algorithms. Has nothing to do with blockchain, by the way. We're a bit older than that. But I mean, obviously you can apply Imandra to whatever you want. But I'm really going to be talking about old school financial infrastructure that runs sort of global markets, which is, to me, actually, surprisingly, shockingly interesting. So, okay, what is the problem that we're addressing here? And by the way, I'm going to be talking about the application domain and the uses of Imandra here. There's a whole other side of it, which is, building a formal methods company. And what is that like? And so if there's any of you who have hopes to do that and want to talk about that, we can talk about that too. That's a real roller coaster. But what is the core problem we're addressing when we apply Imandra to finance, right? Fundamentally, financial markets have become unstable. There are flash crashes, these systemic events typically caused by interdependence of complex trading algorithms. May 2010, drop of $1 trillion in US equities markets. Big ones, we hear about from time to time. Certainly they're not going away. And there are small sort of micro flash crashes regularly in various markets. Big one that we really care a lot about is lack of transparency. So this is where, somebody will have a so-called financial product that they advertise. And of course, these days, most of these things are very complex algorithms under the hood. And it's very, very easy, even if you're really trying hard to be correct, it's very easy to misspecify. Tell customers you're doing one thing, but you're actually doing something else. Especially in the wake of machine learning, there are many examples where, trading system will describe the way something works. They will get it wrong. Maybe it'll be right in most cases, but it'll be wrong in some. And people using certain machine learning algorithms are able to find the things that weren't described and exploit and jump the queue and do unfair things. And, typical example here in the world of dark pools. Is anybody familiar with dark pools? Okay, I'll tell you a bit about them. But basically, they are kind of like stock exchanges, but they're run inside of investment banks. And there are lots of issues classically with transparency there of, BlackRock getting a better price than Texas Teachers Pension Fund, or something like that. And that should not be the case. And so how do you actually analyze those systems? First of all, to make sure they satisfy various, fairness and correctness regulations, but then also how do you ensure the way they're described to regulators and to clients is really correct? How do you reconcile that documentation with the production system? Lots of interesting questions there where formal techniques can say a lot. And then, of course, the kind of catch-all class of glitches. And a famous one is Knight Capital's losing, $400 million in, I think, 30 seconds or something like that for an issue of pointers with linked lists. And, just basic stuff that is really hard sometimes to get right in a massive system, especially with lots of subsystems interfacing with each other. And, you need support. It's not that people are not talented or intelligent. It's that these systems get large enough, complex enough, you just can't do it by hand. It's just not possible. So goals really for this part of the lecture are to teach you a lot of concepts just at a high level, so you can know what we're doing when we're looking at formal models of these things. Venue, exchange, dark pool, order book, order types, matching logic, market microstructure, smart order router. Do you think it's feasible? You can have an idea about all of those by the end of this. A little bit around what regulations are like and where formal tools play into this now. And finally, we'll see, but in practice, to be able to write, something like a simple model of these things, or at least get started doing so, and ask some questions that are inspired, let's say, by these kind of regulatory issues. All right, so there are a few intuitions that I hope you walk away with, and these really motivate a lot of what we do in this space. And the fundamental thing is to think about what we call venue matching logics. I'll tell you what that is, but really to think about those as the instruction set architecture of the market. So at a high level, basically, a matching logic is the way a stock exchange or a dark pool, a trading venue, the way it operates. You can send it instructions like, buy 100 Microsoft shares and at most $50 a share. So you can send that as an instruction, and that's sent using something called an order type. So an order type, like I just said, would be called a limit order, where I have a certain amount I want to buy. I set a limit on how much I'm willing to pay per share, and that's a certain kind of risk I'm willing to take, and I can send that order to a trading venue, and then it's its job to basically try to fill it, to try to find somebody on the other side who's willing to sell something to me in a way that adheres to both of our constraints. So that's a big thing. And basically, there are a ton of these. I'll show you some examples. And really, you can think of them as being, in some sense, the infrastructure, the low-level infrastructure of the global markets. So we import a lot of ideas from hardware verification to this space, kind of based on this fundamental intuition that these matching logics really are like an instruction set architecture. So, okay. And basically, as we go through this, I hope you will leave believing that there's a pressing need for these trading venues, which really are the arenas where trading takes place. There's a pressing need for them to be bulletproof with respect to safety and fairness regulations, for these now very complex matching logics to be formally described to both regulators and market participants, for matching logics to be formally analyzed, and ultimately, for any PhD students in the room looking for cool topics, there's a need really for new financial mathematics that takes this kind of actual semantics of the venue matching logics into account. You have this just wild, chaotic, discrete structure at the lowest level of these systems. And the way most financial mathematics works is it completely abstracts away from the real complexity, the real discrete chaos, let's say, that is the collection of all these different order types and how they work together. And you use, beautiful things like stochastic calculus and Ito integrals that ultimately just completely idealize away a lot of the real discrete semantics. And we need new financial mathematics because it's that at that level that financial regulators typically work and develop regulations. We need new financial mathematics that takes the real precise discrete behavior of these systems into account. And we argue that can only be done by incorporating formal tools because you can't do it on paper. Okay. So, right. What is the kind of landscape of modern finance, let's say, modern capital markets? We like to think about it, arranged in a stack. And again, this is very much motivated by a sort of hardware verification analogy. So at the lowest level, you have the trading venues. These are things like New York Stock Exchange, London Stock Exchange, Borsa Italiana, the big ones that we're all used to, so-called national exchanges. But then you have a whole zoo of smaller trading venues, dark pools that are run inside of investment banks, other things called MTFs, multilateral trading facilities. But ultimately, these are the systems where trading finally takes place. Okay, but we can walk up the stack, and then you start to have these higher level systems that are depending on these lower level subsystems and, effectively depending on abstractions that they have of them. So you have at the next level, things called smart order routers, and a smart order router or an SOR. This is a system that may be connected to, 200 different venues at any given time. It's tracking the behavior. What it can see is happening at those other venues, because certain information of what trades are happening is made public and made public quickly, so-called market data. So it's tracking all these things. And then the goal of a smart order router is, if you have a client who wants to buy 1 million shares of Microsoft, something crazy. Well, if you just sent those, 1 million shares, order to the market, that's going to radically affect the market, right? The price for Microsoft is going to go up like crazy. It has so-called market impact. So what smart order routers do, it's kind of like a game of poker. You are keeping your cards close, and smart order router is trying under various notions of optimality, it's trying to break up your large order into a bunch of different pieces, send those different pieces out to these 200 different venues in different ways to minimize market impact, let you accomplish your goal before the market moves against you, and so on. And that developed very naturally. You can imagine a lot of very smart computer scientists involved in trying to optimize this stuff. And then the regulators came and said, well, wait a second. Yeah, you say you're doing all these really smart things, but what if you're actually making things worse? And so there's a whole collection of regulations called the best execution regulations, all around how it's okay to be smart as long as you're not stupid. You can't have given a client a worse result by being smart than if you had done nothing, for example. So all sorts of things around making sure that stuff really abides by regulations. And then as you walk up this stack, really it's at this level you have what people normally think of as the sort of trading algorithms, where, a quant who is a physicist who's now thinking about swarms of bees and the way those work, and whatever inspiration they get to come up with some crazy new trading algorithm to generate alpha to make money. That's really at this higher level. So that's where machine learning and all sorts of financial mathematics and so on will take place. But no matter what, it has to serialize its intentions down into some instructions that go to a smart order router. And then the smart order router has to then serialize those into a bunch of instructions, a bunch of orders that go to venues. And so basically, as we walk up this stack, we are extremely high frequency at the lower level. I mean, this can be microsecond latency. And as we go up, we get lower and lower frequency. And similarly, on the mathematical side, this low level, venues perspective, that is, highly nonlinear, but discrete, right? At this level, this is, you have fixed nums, these things there's nothing really fancy going on, certainly from like a continuous or stochastic mathematic perspective. This is like, pretty much as discrete as it gets, although you can do obviously a lot of computation there. But as you go up, then you have this, you have more and more abstraction, and you have what people tend to think about as this financial mathematics. Okay, so how are we doing? All right, just to show you, at the level of venues and smart order routers, what is the time scale here? Yeah, you're seeing it there. That's very, very fast. And this effectively connects to these best execution regulations. So basically, some trading venues like dark pools, there are regulations that say they actually have to connect to external public trading venues, track the prices that those public venues have. And if ever they would match a client internally at a price that would be worse for the client than if the client had sent their order to the public exchange, they have to route the order there. And anyway, so this is showing you traffic between a little securities information processor and some different trading venues that are communicating with each other. This is a zoo, right? And all of these systems can have radically different order types, different what are called matching logics. So, okay, I'm going to show you, this is about to go off, but I'm going to show you effectively what a venue is, just a little bit, and then let's take a break and we'll come back and continue. But basically, yeah, what is a venue? The big ones. There are probably a lot you haven't heard of. And ultimately in the US right now, for example, I think there's 65 regulated trading venues. And basically, up there, those are the, so-called lit exchanges. Those are the public ones that have to make their trading, public, called lit liquidity. And these lower ones, these investment banks have their own trading venues inside of them. And the top is called lit liquidity. This lower is called dark liquidity. Liquidity basically are the orders around that can trade. The more orders are there that allow trading to happen, the more liquid things are, the more fluid this trading can be in a sense. So why is there dark liquidity? Why does this exist? Basically imagine you are at Morgan Stanley and you have, one desk inside the very big bank with a client who wants to buy a bunch of Microsoft shares. There's another desk in the bank that has a client who wants to sell a bunch of Microsoft shares. Very natural question is, do you really have to route those orders out to the public market? Because these are both clients of the bank. One wants to buy, one wants to sell. Why can't you just match them internally? And so basically dark pools came about to facilitate that. It's, nefarious as the name sounds, there's nothing inherently unethical about that. But you need, at least I think, but you need a lot of regulations around it. And so regulations like best execution say, yes, you can do that, but clients can't get a worse result than if they had gone to the public market. And this is now a huge part of global finance. And after the break, we'll now talk about where formal methods can come in and where it makes a difference.
Sorry, what's the advantage of doing it in the dark pool? Surely you would just go with the person buying will go with whatever best deal was available, even if it was that person, and same for the seller. Why would you always want to keep that within the bank?
Great question. So it's really, there are multiple reasons. The biggest is market impact. Because if if this is a big order, let's say, if they go out to the public exchanges, anything they put on the public exchanges is public. So then there's a public, what's called an order book for New York Stock Exchange that anybody with a Bloomberg terminal with a feed there can see. And so then the public would know, ooh, a whale wants to buy all of this Microsoft. So then the price goes up. And so the idea here is you can make this deal together. There's regulations that say the deal can't be bad for the clients, but it minimizes market impact. And there's also other things, transaction fees. So it's also better for the bank because it costs their transaction fees to go to the public markets. That eats into everybody's profits. A lot of reasons.
Cool, thank you.
Yeah.
I just know nothing about this.
Yeah, no, my pleasure. Okay, shall we take a break? Cool. Oh, thanks. We'll get to analyzing algorithms soon. Attention. And then ultimately, if we can show them how to fix it and then verify that the fix is correct, then it's just it's a different ballgame. So that happened nicely for us early on. UBS, the investment bank, had one of these dark pools in the US. And basically, they, complex matching logic, as these things have, that was actually approved by the US regulator. And the issue there is, the US regulator looks at it, tries their best, maybe does a little MATLAB and does some things on paper to think about edge cases. But without formal tools, the state space of these systems is just too complex. So they say it's okay. And then, of course, there are subtle issues that were missed. And in this case, 4 years later, the regulator came to UBS and said, actually, we noticed by looking through post-trade data that there were some really bad prices that you gave to clients for a long time. And they fined them. It was a $14.5 million fine by the SEC for issues of unfairness. The kicker being that the design had already been approved, but it doesn't matter. And basically, that was a very, it was bad for the bank. It was bad for the government. 4-year investigations, very expensive. And ultimately, our point was to say, wait a second, if instead of finding these issues 4 years later by looking through post-trade data, instead of doing that, you just formalized at the very beginning the design, then we can check for these issues at the design phase. Of course, I know I'm preaching to the choir here, but that's the point. Let's catch these issues in advance of allowing these systems to be deployed. And so UBS had a competition. Normally, we wouldn't have had access to all of these things. Stuff was made public. And then we ultimately showed how Imandra could find these issues in 30 seconds on a laptop, versus 4 years sifting through post-trade data. And that got attention, and that actually brought us our first, institutional venture capital investment, and so on. So finding these ways to these kind of weighs in strategically made a big difference. And I want to show you what this looks like. So basically, when you are an investment bank with a dark pool, you have to, in the US, I'll describe, you have to submit a form. It's called Form ATS, or now it's Form ATS-N. And this is, in English prose, a description of your matching algorithm, of how your dark pool works. And so it's one of these, lawyerly documents that has, ultimately a lot of boilerplate, but then it's actually describing a very complex algorithm. So I want to show you how you can play with this. If you go to our docs, go to Imandra Core, and I'm going to go to examples. I'm going to search for UBS, analyzing the UBS ATS dark pool, and I'll launch. Let me launch here Imandra on this, and I'll look for a UBS Form ATS. Let's see. So you can go and actually see these regulatory documents, and actually take a look at them. They're available, lots of interesting complex algorithms described by lawyers in English, which is crazy. But ultimately, so what we did was, this is very, very early days for us before we had DSLs, but I want to show it to you because it makes all this stuff very concrete. And then I'll show you what these DSLs on top look like. But basically, we have to now encode the structure of a dark pool. Really, you can think about it as you're building an implementation of it. It's like a simulator, but because it's actually in Imandra, it also is a mathematical artifact that you can analyze. But first and foremost, it's really a program. So it's a program implementing the logic. And ultimately, what does a system like this look like? Well, it has to effectively have a market data feed. So the key things to know about this market data feed, these are, ultimately I'm modeling them here as real numbers. There are different decisions you can make. But the most important things there are the so-called NBB and NBO. So these, if you remember a dark pool, it can do these internal trades inside of a bank, but it has to keep track of what prices there are at public exchanges. And if there's better prices for clients, it has to route the orders there. So this is how it does it. NBB is national best bid. NBO is national best offer. And so for each security that's traded here, it's keeping track of, what are the best prices available. And it has to actually use those as part of its pricing decisions. And then you have different market conditions. These are really across global markets. These are normal things, so-called normal market, crossed market, or locked market. And then some other calculations. Which market are you in? If the national best bid and the best offer are the same, that's called a locked market. That's not good. There should be a spread. Basically, I'm going to define these things. And we could see, for example, like which market are we in? It looks like this. That's the so-called crossed market. The key thing is I'm building up a mathematical model of this system, but it's just code. Okay, now I'm going to define in program mode. I'm going to do some arbitrary OCaml, and I'm going to define some custom pretty printers. And then I'm going to tell Imandra to go back into logic mode. Forgot requires lockdown from here. Oh, well, it's okay. And then we'll define some other things. We're going to model time as an integer, price as a real, some static data. It's actually going to include floating point as a reason for that, for the so-called tick size. And now here's just starting to get some quotations from the regulatory form. So the regulatory form says, here are the order types we support. We support pegged orders, both resident and IOC time in force. Pegging can be to the near, midpoint, or far side of the national best bid or offer. Pegged orders may have a limit price. Then it supports limit orders, market orders, and finally supports these things called conditional indications. So we don't need to go into too much what these things mean, but I want to just give you a flavor, like why are these things complicated? Well, basically, and I mentioned there's something like 65 regulated trading venues in the US. Why would someone decide to send, their order flow to trading venue 62, right? Why send it there? And that always trading venue 62, it's trying to incentivize people to use them, to send their orders there. Order flow begets order flow. And so a lot of what these, companies do is they introduce new innovation, which is a new order type. In a sense, it's like a new instruction for a processor. And it's a new way that somebody can trade on their system and package risk. And basically over time, these have become, you know, little programs, and you can put them together in very complex ways. And so here, you know, these look pretty simple, like limit orders and market orders. A market order says, you know, I want to buy 50 shares of Microsoft at whatever the market price is. I have no limit. A limit order puts a limit on how much you're willing to pay if you're trying to buy or accept it, if you're trying to sell. But then you have pegged orders, and pegged orders, basically, these are looking at the national best bid and best offer, and they're computing prices as a function of those. And there's various ways that you can do that that are legal, various ways that would violate regulations. And then finally, you have these things called conditional indications. And these basically allow you to send out a probe to the system and say, I'm thinking about sending an order to do the following thing. If I did, is there an indication of interest on the other side? Would it be worth it? And there's various levels of information you're allowed to get back that then ultimately may make you send what's called a firm up. And that is where you say, okay, I really want to do this. So this stuff really is extremely complicated. And basically, we're now just going to, you know, start building up a system. Think about it as an interpreter for these order types. And I'm just going to race through some of this stuff. Make sure I turned on my timer. Yes. And, you know, as you see, it's pretty complicated. But what we really want, you know, we want our executable formal models ultimately to be things that we can co-simulate against the production system. And we can reconcile them, you know, against real flow. And so that's why we're making this, you know, really a real system. Like order has a lot of information, has an ID, has an order peg, has a client ID. And for example, one kind of fairness regulation we may want to prove is, even though this trading system knows for each order who sent the order, it has a client ID associated with each order, it better be the case that this system never exploits that client-specific information to give one class of clients a better price than another. And we can encode that as a verification goal in Imandra very naturally. You know, we can say, imagine we have two states of the system that are exactly the same up to modifications of client ID. Would the resulting trades be the same up to the modifications of client ID? Okay, so now we start to get into some complex pricing functions. And you can see here this notion of priority price. This takes a side of the so-called order book, which has lists of buy and sell orders in order in the current market data. And it's then looking to see if you have a pegged order, and then it's ultimately computing the price you're willing to pay or willing to accept based on that. So bottom line, just want you to see there's nonlinear arithmetic involved. This very quickly, even for a relatively simple system, you can see why trying to, you know, study the algorithm written in prose is just, it's not a realistic solution to making these things robust. So finally, okay, yeah, we'll define the order book. Order book consists for each security of a list of buy orders and a list of sell orders. And key thing to know, and let me just kind of show you a picture of what this looks like. Key thing to know in a trading system is for a given symbol, for a given security like Microsoft, you have your list of buy orders, those are called the bids. You have your list of sell orders, those are called the offers. And you know, that's why we have a list of buys and sells in the order book. And at each discrete time step, those two sides are being sorted. They're being sorted with respect to some ranking function that ultimately is deciding who is going to be eligible to trade next. And it's the orders at the top of both sides of the book that are the ones who are eligible to trade. So a lot of unfairness in the market. And is anybody familiar with Flash Boys, the Michael Lewis book? It's a great thing if you're interested in this stuff. It goes into a lot of these details. But a lot of these issues of unfairness in the market come down to ways that people are find to jump the queue and get to the top of the list above others, when really it's unfair for them to do that. And you know, there's a fundamental idea, yeah, very complex. There's a fundamental idea here of what's called price time priority. And that is, you know, if I'm submitting a buy order and I'm willing to pay more than you, then first of all, I should be given higher priority, right? Because also this is supposed to facilitate price discovery. So somebody willing to pay more should be prioritized. But then if we're willing to pay the same amount, it should come down to who was there first. So it's a lexicographic ordering, price time priority. That's how people normally think, and there's regulations that say you need to respect that. But in reality, it's much more complex. So if we go back to this UBS example, now here's the fundamental thing, the ranking functions for orders. So here's a copy of the pros from their regulatory filing, describing, the logic. It says, eligible resident orders and IOC orders are given priority based first on price, second on time of their receipt. Eligibility is determined based on the crossing restrictions associated with the orders on both sides of the potential cross. Invites are sent to the order originators of conditional indications on a priority based first on price, second on quantity, and third on the time of receipt. For orders with the same price, priority is given to resident and IOC orders over conditional indications. All marketable limit orders, i.e. buy orders with limit price at or above the national best offer, will be treated as though they are at equivalent prices for priority purposes. As such, they will be handled based strictly on time priority as if they were market orders. Okay, it continues. It's extremely complex. And if we then go to encode it, we end up with a function. Let's call it order higher ranked. And what it's going to do is it's going to take a side of the book, either the buy side or the sell side, two orders, order one and order two, and current market data. And its job is then to decide, should order one be ranked higher than order two? And that ultimately is the function that's going to be used to sort these two sides of the book. And if we go and implement that logic as described, there's a sort of competition between these priority prices, which take into account national best bid and offer and pegging and so on. And then based upon differences in prices, we go down to a competition between time. But then finally, there ends up being all of this complex logic about conditional indications. And that is, it turns out, therein lies the rub. So if we define this, we now can define in Imandra, this is the punchline, what we're working up to, we can define, a very basic property that a ranking function like this should satisfy. And that is transitivity, right? And so we can write this out just as a Boolean valued function, and then we'll ask Imandra to verify it. And that is for all sides of the book, for all triples of orders, order one, order two, and order three, for all possible market data values, it better be the case that if this logic says order one should be ranked higher than order two, and it says order two should be ranked higher than order three, well, it better consistently say order one should be ranked higher than order three, right? If not, and then we go do quick sort with respect to this ranking function, we're going to get junk out. And ultimately, then let's ask Imandra. So I'm going to ask it to verify for all of these input values, this rank transitivity holds. And Imandra comes back very quickly and says no. And so basically, as part of this UBS thing, we showed that the core issues that they've been fined for could have been found in the design. But then Imandra actually kicked it back, because transitivity is something that we automatically check for when you're using our venue analysis stuff. Kicked it back and said, wait a second, this ranking function isn't even transitive, but it's very hard to find this sort of needle in a haystack. If you have three orders on the sell side, order one is pegged to near, and it in particular has this capacity principle in a resident order. Order two is a limit conditional indication order pegged to near that's resident. And order three is another limit conditional indication pegged to near that is principal. And you have this market data, basically, these are counterexamples in Imandra, so they're reflected, we can compute with them. Order one is ranked higher than order two is ranked higher than order three, but order one is not ranked higher than order three. And from this lack of transitivity, you can back out various ways to actually jump the queue.
Two questions.
Sure.
One is for the first year programming students who none of us actually are. But in that code, there was a very spaghetti conditional logic where you test for the ordering and you return +1, 0, or -1, and then you test -1s and return trues and falses. Is that because you have to be faithful to the words, or because you knew that the OCaml would be optimized to make all that shit go away?
Great question. I would say it's a combination of trying to be faithful to the words, writing this in a way that when we were going through it with regulators and people at UBS, they understood, they really weren't used to algebraic data types, but they were used to this kind of stuff, and then also, if we were doing this from scratch now, we've learned a lot. It would be more beautiful, I think. But good thing is, ultimately, it gets compiled into an internal logical representation that, which I think comparable to reason about if it had been written in a more elegant way. But we all, there's this tension often where I'll show you next too in this DSL that we have for higher level stuff in finance, a tension between trying to be faithful in the way people currently talk about things, trying to be faithful to that, and trying to incorporate what we've learned in programming languages for 50 years, which often are at odds. Yeah, great.
That's the programming question, now it's the math question. So transitivity looks like a good property to have. But are there ever situations in this kind of domain or these kind of scenarios where you get some kind of Arrow's theorem that says transitivity is impossible? You can get 2 out of 3, but you can't have this.
That's a great,
Impossibility.
yeah, great question. They're not directly related to things like, well, not directly related to order ranking stuff we've ever done. That maybe there could be something there. But definitely when it comes to pricing. So order ranking is one piece. It's basically deciding who gets to go to the ball game, right? And in what order. But then you have the actual pricing logic and deciding exactly what quantity of things are going to be filled in what way. And that can, there a lot of systems now do things called continuous auctions. Right. And effectively, these different kinds of auction mechanisms can involve, dynamic programming. You can have, in a sense, a real optimization problem for deciding the price of things where you can get impossibility theorems for sure. Yeah, a very cool question. Okay. Oh,
Let's say I have a tech order. I use the map. I'm using Imandra, and it checks an algorithm that usually it was checked by a person, or a person just knew how to solve this book. Now, you implemented the algorithm from English text into Go, and kind of the translation there is sort of now the machine just decides. Right? But how do you verify that the translation of the English text means
what you think it means?
Yeah, so my take order does still now it means something else, right? Than it would have in the original line.
Fantastic question. And let me answer that with a next section. Great question. So the question is really, okay, we just showed, taking something that's informal, formalizing some aspect of it and analyzing it, which is a lot, of what you have to do when you really want to apply formal verification. But how do you then close that gap? Because of course, just as you can make mistakes in the design, you can make mistakes in the formalization. And then also, how could that possibly be connected to an implementation that's running in practice? So I'll take those as related questions. And this is not unique, of course, to formal methods. Any mathematical modeling suffers from things like this. And, the analogy I love of a computer-aided design tool like Autodesk Bridge Builder and designing a bridge, right? They have this amazing situation where you can design a bridge in this piece of software, push a button, and have hundreds of years of engineering mathematics analyze it for safety in various ways. And then, great, you get out, print out instructions of how to build this bridge, civil engineering blueprint, and you give it to an amazing team who goes to build it. But of course, how do you know that they built the right thing? You can't just like compile and spit out the bridge. Well, maybe you could, maybe one day. But ultimately, you still have to close this gap in a sense between the mathematical model and the physical world. And so basically we do that in a process we call auditing. And I'm going to get there, but I just wanted to show you. So this like zoo of order types, we looked at a few, but I mean, it's amazing. So you see headlines like this pretty often. Simplicity is the goal of NASDAQ's new order type. What was this one called? Hide not slide. Yeah, hide not slide orders were slippery and hidden. SEC finds exchange over queue jumping orders. So this stuff, for there to be a fair arena for this global finance to take place, this stuff has to be bulletproof, and it classically is not. But now let me show you to your question. So basically here is the life cycle of really what we do in finance. And it's really this last one we call auditing that closes this gap. So the first that we've seen is modeling, and a key thing here, there's again a critical design decision for Imandra, was making these formal models executable and efficiently executable. So, as you noticed, we put in a lot of detail in that little model of UBS. And we did that because we want this to ultimately be something that could be a simulator or perhaps an implementation of the real system. And that's going to be very important for auditing. So, but basically, we started modeling, and there really should be, in a sense, a direct arrow back also, verification modeling, because this goes, you're modeling, you're trying to verify properties of it over and over and over again, getting counterexamples, ultimately reaching a point where, okay, now you believe that your design is good. All of your 200 verification goals derived from regulations and internal requirements and so on are met, are proved. Great. And in real world, that could be many months of design iterations to do that. Then let's say we make it to the testing phase. So here, there's really a bifurcation. You could take the verified Imandra code and use that in production. But of course, you're still, currently you're still trusting the OCaml compiler. You are trusting, of course, the operating system that it's running on. You're trusting the hardware. So even if you're using verified code in production, there's still so many things that can go wrong, right? The mathematical model is only about one piece of this, a very important piece, but you got to remember it's not a silver bullet. So that's number one. The other option is that there could be an independent third-party implementation. And this happens a lot. It kind of goes against the dream of formal methods of, using the correct by construction or formally verified system. But these things are messy. And a lot of times you will have an independent third party who's a trusted one in the space, like NASDAQ or Euronext, will actually be hired to do the implementation. And so in that case, and this is stuff that we do, they will use the verified Imandra model as the spec. That's the gold standard spec that they then use to implement the system. But that's a totally separate implementation. So how could we ever know anything about that? So the next piece of the cycle is testing. And this is really model-based testing. So because we have this, mathematically precise, verified version of what the system should do, we can analyze that in various ways to create test suites that ultimately try to push the system into different edge cases to, it's not going to be proof, but to gather evidence that the system is properly implementing the spec. So that's done next, and I'm going to show you the kind of key technique underneath that, what we call region decomposition. And then finally, let's say, so that will find a lot of bugs, you iron those out. Finally, everything looks good, and then you go live. And here is the key thing for closing this physical gap between the mathematical model and the physical world. And that is because our model itself, first of all, is designed to be faithful to the actual production system in the sense that it takes exactly the same, has exactly the same API, processes the exact same kinds of messages and sends out the exact same kinds of messages that the production system should, and it's efficiently executable, we can then co-simulate them. We can run them side by side, and that's effectively what we do. And so then the verified formal model becomes an auditor. And, for example, every morning, Goldman Sachs wakes up to a report about, did the production system, did every observable behavior on the production system, every trace that went through it, did it actually reconcile with what the verified formal model says that it should have done? And if it doesn't, then that needs to be flagged up immediately. And then we have various tools to go find out why. And there are many, many reasons that could happen outside of, a bug in the code. It could be that market data feed was delayed. It could be, again, an operating system failure, hardware failure. Doesn't matter. We need to know that it ever differ from what the verified formal model says it should be. And that then, from an engineering perspective, you have this information about things not being right, at most the next day, and in various ways it can be basically live, as opposed to 4 years later, a regulator knocking on your door and saying, oh, you did this thing wrong for 4 years. So that's, it's not doing everything. It's not, ultimately in that case, proving the production system is correct. But what it's doing is it's proving that every observable behavior that actually went through the production system is correct. It adhered to what the formal model says it should do. So, okay, I want to show you what these things look like. We only have about 15 minutes left. And, here's where we've really had to develop products. So this is another thing for anybody, wanting to do formal verification in industry. The kind of gulf between being consultants who come in and help do something, the gulf between that and actually having a product that somebody can just use and you can license. I mean, that is a massive one that took us much, much, much longer than we thought it would. And the key really for us has been finding these niches, that are really specialized, where we can just have something that it's a very restricted domain. It's a real pain point and it can just work. And, you're not going to be able to encode something crazy. It won't let you, but it can work for what it needs to do. And so I want to show you first what this looks like for connectivity. So basically, let me tell you the kind of map, what this is showing here. So we've been talking about these trading venues. That's what we call systems. And of course, these trading venues have to connect to others. And there's a protocol that's used in finance. It's called FIX, Financial Information Exchange. And basically, everybody in finance has the right, and most do, to modify this communication protocol. They modify it to support their own special order types, special other features that makes their system unique. And so when you are, deciding to go trade on one of these systems, you have to be onboarded. And that includes you studying what's special about their version of the communication protocol, and then going through a bunch of tests to try to test that you properly understand how to talk to them. And so what we've done there, this is a huge problem in the plumbing of the markets, making that stuff correct. And classically, by the way, these connectivity specs can be hundreds of pages. And so what we've done there is we have a domain-specific language called IPL, Imandra protocol language, and basically this is written in Xtext, this framework we talked a little bit about yesterday. This is, let me see if I can find a cool one. Yeah. This is a domain-specific language, really tailored. Might make graphics not look good zooming in, but let's see. Tailored to this particular need in finance, this financial information exchange protocol, and all sorts of IDE support. Basically, the user just has to write what is special about the state of their system. They define what kind of messages they support, what are the required fields, what are validations on them. These are things that previously would be written in English prose. But crucially then, once you do this in this high level language, this model ends up being 300 lines basically. Once you do that, Imandra can then decompose the state space of this system using this technique. Can I move this thing? Technique called region decomposition. And basically what this has done has shown us for the life of an order, starting here in this pending new status, what are all of these unique symbolic ways that users could submit messages to cause the state of the system to evolve. And this is computed automatically using this region decomposition technique. And basically then what we can do, this is for the case of onboarding somebody, we need to come up with tests. We can then say, okay, here are all of the unique symbolic behaviors. The user needs to be tested on all of these. But let's say I want to create a test pack for their first one that just includes these. Then I can do that. And the crucial thing is for each of these regions of behavior, Imandra then synthesizes a test script. And so there are various, tools used in the industry for doing these kinds of tests. And classically, people write the test by hand, by going through these specifications of the protocol, trying to, think about what the edge cases are. It's laborious. The kind of average was typically 4 to 6 months to create these test packs. And now all we have to do is just mathematically encode in this high level language a precise version of that spec for the protocol. And not only do we get all of these edge cases enumerated with rigorous coverage metrics, but we synthesize automatically these dialogue-based test scripts that then, you can just spin up a testing environment in the cloud, and then the client can go and onboard that way in a self-serve way. One cool thing about this too is this actually, is anybody here doing stuff related to quantifier elimination? Okay, cool. This necessarily uses quantifier elimination because this sequence of events is pretty simple. But imagine we had a sequence of events where you got a new order and you had 2 fills, for example. A fill means at least one trade happened. Well, basically what we have to do in this computation of a test script, we have to then back out the fact that whatever order is submitted must have at least quantity 2, because we couldn't actually complete the sequence of events and of having multiple fills unless there were at least 2 orders, for example. And that becomes naturally a quantifier elimination problem. There exists some number, some bounds such that the whole sequence of events can happen. So there's, lots of fun stuff involved in actually synthesizing these test scripts. But basically, this is the foundation of now how we do model-based testing. And finally, let me show you what this auditing looks like. And obviously I'm showing you all this stuff focused on finance. My hope is, this gets translated, I hope, pretty directly to other things you're interested in, because obviously this whole approach of modeling, verification, testing, and auditing, I mean, you can apply that to almost any complex computational system. So basically here, this is now back to this trading venue case. This is actually auditing what the behavior of the real production system was using the verified formal model. And let me show you what that looks like. So basically, this is going through every single day, looking at all of the actual flow that went through the real system, and then ultimately reconciling that against what the verified formal model says it should have done. Might take a minute to load. And you can then do queries over this and say, was there ever a sequence of events where a wrong price was given? For example, those, of course, get alerts and so on. And if there is, then you can actually walk through and, and obviously this looks quite technical, but this is in the parlance, basically, of one of these market practitioners. They're used to seeing things this way. So this is really a domain specific interface, but basically you can walk through each of the state changes to see exactly how the system evolved when you actually have an incorrect event. So there's all sorts of, cool stuff that you can do here. And yeah, here we're looking at events where you have orders filled. But for example, we might want to see events where we have mismatched auction prices. There's my little button. And basically now, anytime there is a mismatched price where the production system said, computed a price one way and the verified formal model says it should have been something else, now I can actually go into one of these events and actually see, and I can directly now using, in a sense, the explanation that's coming from the logic of the verified formal model, I can see, how these bad things were computed.
Say a verified formal model is that, it must be the properties that you're talking about on the program, as opposed to the program itself.
It's the program itself. So basically, you have the program itself. Remember, in Imandra, the first thing you have is the program, right? That's your mathematical model is a program. So what you have first is a real faithful implementation of what the production system is going to be doing, and then you verify all sorts of properties about that. But once those are all verified, now you have this verified formal model as a computational artifact you can use to do this kind of analysis.
But would you say that the verified formal model is the actual properties that you verify as opposed to the program?
No, I'd say it's the program. The verified formal model is the program. You have lots of things you verified about it, which are now, really useful information.
I feel like the properties that you actually verifying would be what you call verified formal model, because those are the actual things that you've encoded and those are things that you've proved. So,
Yeah, I mean, definitely, I would say that doesn't make sense in our setting really, because we can take it offline, but the key thing is that you have this model that is itself programmed where you've proved what you care about about that model. And now you use that model itself to audit other things. Because you easily could have properties that you proved about the system that do not pin down the system at all, right? So that's not, the properties themselves aren't enough to actually have the model. You really need the program itself to have the model. But the properties, of course, are the nice things that you've proved about the model that you now know are true. But we can,
Will the
you know,
program have more behaviors than specified in the problem?
sorry, say it again.
The program will have more behaviors that's been actually verified.
I mean, yes, you definitely could, you know, I could define a sorting function and, you know, prove that it sorts, but maybe also, you know, it has some other thing where if it has values that get mapped to, you know, the same, well, who knows, whatever. There can be many things that are not specified for sure. So it's always you know, there's always a question, do you want to specify more and verify more things of the verified formal model? But definitely, yeah, the model itself, in Imandra, a model is always a program. It's not properties really, it's, you know, a program of which you're doing verification. On which you're doing verification. Cool. Okay, I think that's about it. But yeah, you see, you know, observed data did not match the model, and you can actually go through, you know, we could go through these different state changes, see exactly how the system is evolving. This is an order book evolving. And this kind of, you know, really explainability interface that's domain specific, but it's informed and really driven by a verified formal model. That's, you know, utterly critical, you know, I would say, in ultimately closing this gap between the mathematical model and the physical world in a useful way. And finally, I'm just going to add one last thing for anybody wanting to do this sort of thing in industry. One lesson that we've learned, and that is, you know, we normally think of formal methods as something that we sell, or, you know, we do for safety, from the perspective of business, it would be like compliance and cost savings and, you know, mitigating risk and so on. And that's core, right? That is so crucial. But one thing we've learned is, if you can find ways to also have so-called front office intelligence come out of what you're doing, it can be a lot easier to get people over the line to want to use it. And so one of the things that happened to us over time is, because we have, you know, here we have this verified formal model that we're running against the real production data. Well, we then have some really compelling information. We have the possible behaviors that the system could have in terms of the actual state space of the verified model, and we have what clients are actually doing. So we can analyze those in tandem to come up with recommendations. And so that's what you're seeing here. We call these venue insights, but basically, you know, there's a whole query language here now where we can analyze things. They're really counterfactuals. Like, okay, you know, we effectively saw yesterday that, you know, clients had size deltas that looked like this. But is there some size delta that they could have used that would be different, where they would get better performance? And because we have the formal model, we can basically consider alternatives they could have taken, other order types they could have used, other parameters they could have set in different ways. And then we can, in various ways, try to optimize over that and actually extract actionable intelligence that tells people how to get better performance. And that has really been a game changer for us, because then it's not just, you know, compliance and cost savings saying we need this. It's also front office people who care maybe less about the back office things. They realize they get very useful insight out of it. And, you know, then things just kind of gravitate towards everybody understanding they need formal tools. Okay, one question.
Do you guarantee that the properties that prove will be an over approximation of the behavior program? Like a sound approximation?
No, I mean, you can, any Boolean valued question you have about your system, you can pose, right? So there's no, I mean, what we guarantee is that if it's proved, then it's always true, right, of your system. But this is not, you know, it's not an abstract specification language where your system is somehow a solution to an abstract spec. Your system is a very concrete spec, which is an OCaml program. That makes sense.
Have you formalized all of Allo's theorem in some of the tests that you've done?
What was that, sorry?
Have you formalized all of Allo's theorem in some of the tests that you've done?
Arrow's theorem?
Yeah.
Have we found instances of errors theorem in tests that we've done?
Yeah. Like,
Interesting question. I don't think so.
because if you have like a social choice function, then you can simply just like apply Allen's theorem onto it to see what properties it satisfies.
Oh, are you talking about specifically for things that are related to like voting mechanisms? Or-
Could you repeat that?
Pardon me?
Could you repeat that? Please?
Like are things that we could cast as sort of voting mechanisms?
Not just voting mechanism, anything that has a lamp order.
Interesting. Not that I know of, but it'd be cool if you can explain more of your question to me later, because I don't think I totally understand. But maybe high level version of your question. Do we observe interesting properties that we didn't know about the system and we didn't verify by looking at the real production flow and all the time? Yeah, and so there's this query language. Basically, more and more, we're trying to make it easier to sort of find these emergent properties that we keep seeing in various ways. And one of the things we use here is this Imandra Discover conjecture synthesis tool that I just briefly talked about yesterday, but there's a notebook for it. But basically, finding various ways to try to come up with a compressed description of interesting phenomena. That's a very cool question. We try to do it in various ways, but it's hard and ongoing, let's say. Yeah, sure.
Nothing topic, I guess, but I've never run into like you discover shady property. You don't want to think that it's there. Are we allowed to talk about that?
I will say we have had some crazy times in that way. And yes. I mean, ultimately, we feel like our job is to give regulators and practitioners these tools. And we are pushing, doing our best to lobby and get these regulations to become more precise. And so we have a sort of community effort for various regulations, like in Europe, MiFID II. We have a MiFID II library of verification goals that are, now hundreds of precise mathematical statements derived from MiFID II regulations. And sometimes we know if somebody is violating those, but sometimes, they can just use them and analyze their system, and we may not know. But ultimately, once it's audited and a regulator, is actually viewing this stuff, if it's live, they will know. So, but yeah, maybe offline, we can talk about some crazy stories.
I'm curious, how long did the whole process of finding and fixing the bugs take for the UBS?
Yeah, I'll say in general, for like taking these like real world dark pool kind of things, example, typically this modeling and verification, if it's a new design, maybe 3 or 4 months of iteration. I mean, obviously this is going to depend on the scale of the system, but for these things, that's often what we've seen. And then testing, if they use, some will use the verified Imandra code directly in production. And then the testing parts is usually much smoother. I mean, there's still a lot of other things that can go wrong that aren't modeled, of course. So there are things that are found, but that's a lot smoother than, independent implementation in Java, right? And so depending on how that's done, that may take a couple more months. Often that's where like concurrency bugs in the middleware come in, there's all sorts of stuff. But once that's done, then it's really the auditing that it's, every day giving everybody assurance that, because also part of this process is now deriving the documentation from the verified model. That's a big thing. And, really having a way to keep the documentation in sync with changes to the production system. So that's a part of this that now is first of all, it's much more robust and it's much quicker than it used to be. Like that, that fixed stuff that we were looking at for the protocol, I can go back and here we can actually generate the documentation that would go in a PDF. And these get traced back. These are documentation artifacts that get traced back to the verified formal model that is then audited against the production system every day. And so, it makes a lot of things much shorter, but there is an initial investment to say, hey, okay, I need to spend time to get this right, and this is going to take months typically.
well, let's thank John for.
Oh, thank you. Thank you.
The last show for today, let's have James and Elizabeth for their for. In 2 days, we have a complete program with James and Elizabeth John giving their talks. Tomorrow there will be a new set of lectures starting. Our fathers here, Southern Gujarat, and then the Sam will also join them. And Jerry, so it's kind of pretty set from this meeting, and there will be something new coming tomorrow, so we have 13 week left. I promised you group photo, and I have an idea. I think to save time, we'll just do it here. We'll switch on the lights, and we won't have to walk anywhere. And also, we have the advantage of the layered landscape here, so we can just send and do a quick group photo now, and then if needed with another set of lectures, we'll do another one. So maybe 2 group photos. We'll see. But please, if you just gather somewhere in the middle, I will try to use my wide range of
Oh, hi.
Yeah.